Hello and welcome to the Cold Finish Steel Bar Institute's teleconference seminar on the state of the art of cold finishing. We are coming to you from teleconferencing centers in Chicago, Illinois and Pittsburgh, Pennsylvania.
He is president of Glen Carbide, Carnegie, Pennsylvania, which was founded in 1959. Past president of the Society of Carbide and Tool Engineers International, and past president of the Wire Association International, with a BA degree from Denison University. And assisting Ken is Mike Kennedy, their sales engineer at Glen Carbide. So with no further ado, I'll turn it over to Ken.
Thanks very much, Bill. I didn't exactly know how to take it when he introduced me earlier as an old friend. The only thing I could say to Bill is that with our gray hair, I think we look pretty distinguished on the monitor. I want to talk about the state of the art in carbide dies. Thanks very much for asking Glen Carbide to participate in this seminar. This type of informal yet educational program can go a long way in helping North American bar mills keep abreast of the state of the art in cold finishing. This type format also gives me a chance to talk to you about a lot of things regarding dies that need said, and many of you would not have time to listen to if you were not attending this seminar. We're going to express our opinion regarding the present state of the art in carbide dies as related to their usage in bar mills, and we hope it motivates you into making some improvements. Carbide dies are the heart of your cold drawn operation, but most likely not very high on the priority list for many of you compared to other items such as we just talked about in grinding, turning, or straightening. To most drawing applications, a die is a necessary evil. Yet this was written about the carbide die years ago by Alan Dove of Stelco. The drawing die has been aptly described as being outstanding among all mechanical devices employed by man, in that it presents a very remarkable combination of simplicity and effectiveness, causing plastic flow of metal, which provides elongation and reduction in diameter to a degree obtainable by no other method. It changes the physical properties of the material and provides a degree of accuracy of size and section obtainable by few other methods. To the metal, it imparts a dense structure, a hard surface, and a high degree of polish. It becomes an automatic testing machine which detects flaws in the metals, announcing them in terms of pickup or breakage. All these functions it performs with no other aid, apart from the lubricants and coatings, than the force which pulls the material through a stationary die. That statement is very true and emphasizes the importance of the die in your operation. However, since there has never been a lot of literature available or educational courses presented on dies, they have remained somewhat of a mystery. You can have a metallurgical or engineering background, but never have been exposed to the intricacies of carbide dies. Therefore, you can easily feel inadequate when it comes to making intelligent decisions regarding proper die design, analysis of drawing problems relating to dies or how to solve them. Because this gray area exists, many mill supervisors, all the way up through superintendents to general managers, do not get involved very deeply in dies. Sometimes decisions are passed off or delegated to people too far down the management ladder to make qualified decisions. We see this every day where bar mills make poor judgments in their usage of dies. There is a need for improvement in the present state of the art, or to put it more bluntly, how can we think about more modern drawing techniques when the present die practices in a lot of mills are not satisfactory? There is a big problem out there in the quality of dies being used and maintained in the mills. Yet, in many cases, management is unaware of the problem. Management assumes their die practices are adequate when in reality they are horrendous. On the other hand, where management is die conscious, you usually have a good bar mill operation. No mill is going to operate efficiently today or even stay in business adhering to the die practices that have gone on for years. Here are some other areas that should be given some attention. Prints, or should I say lack of, or outdated. Mills furnish prints only of the required shape. Complete die design is left to the die fabricators. This is fine if you can trust your die supplier, but even then, there can easily be misunderstandings. This is even worse when die suppliers are competing against each other with no prints. Nib heights, nib outside diameters, bells, angles, back reliefs, bearing lengths, and steel casings can all turn out differently. Tolerances. They can be non-existent or too loose as in this example. How can a die maker be expected or know where, when furnished a print as shown on the screen here, where to make the die? Typical examples are expecting dies to be made to draw to the low limit on a particular grade with no input from the mills, or at the other end, tolerance listed in 4 decimal places for no obvious reason, or accuracies of angles toleranced in minutes and seconds. A lot of mills do not keep accurate enough records of what sizes dies draw for particular grades of steel. Die sizes. A lot of mills cannot correctly measure die sizes. They can gauge the drawn material, but not the die. Then, in shape sections, the measurable dimensions can be checked, but not the overall shape configuration. Through the years, there have been endless arguments because many bar mills do not have the proper equipment for measuring. Die room equipment. Not many bar mills have good die finishing equipment. Many have adequate equipment, and some the latest. But the majority of mills have outdated methods for maintaining dies. You may purchase new finished dies, but how many mills properly maintain their dies? Die makers. The present state of the art in die making skills in a lot of mills ranks from poor to terrible. And what is a sad situation is that in the eyes of management, some pretty poor die makers are considered good. There are a lot of situations where the mill die finishers are there because of seniority rather than skill. There are also a lot of good die makers in mills, but they have been there too long, been doing things the same for too many years. They are out of step with the better die finishing techniques. There are also a lot of die makers in your mills that have old-fashioned ideas and will not adapt, even with modern equipment. They are too stubborn to change. A lot of these guys think they are super die makers when in reality they can't make a good die. They take way too long to finish a die, but since management may not know how long it takes, a die maker can set his own pace. We know mills where the head die makers make the decisions and dictate to management the die specifications. This is fine if they are knowledgeable people, but generally the specs are based on what they think happens during drawing rather than on fact or state-of-the-art knowledge. It is a fact that in some mills, the die makers actually do more harm than good. Mill management regarding dies. The problem here is that supervisors in charge of dies or the die room generally have so many other responsibilities they cannot spend the necessary time to run an efficient die program, nor do they have the time available to become really die knowledgeable. When a die fails, proper analysis can usually determine where the problem is and what caused the failure. Instead of a real analysis, the die is rushed back to the supplier with the general opinion that the die is defective. Yet a closer observation taken at the mill could have cleared up the problem or avoided it altogether. In checking, the die is usually not at fault. It only called attention to a problem. Poor stock had been used. The draft was wrong due to over or undersized hot roll. Pickup had not been cleaned out of the die, or the die was left in service too long. This list could go on, and we realized many of these problems can't be easily solved. However, many problems could be solved if someone in your mill had the responsibility, and just as importantly, the time to become die knowledgeable. We are certain a lot of die problems that become our problems as die makers and cost mills thousands of dollars could be avoided if someone had the time to get into die problems. How many supervisors can look at a die and tell if it is a good die? Do your supervisors know what angles and bearing lengths dies should be? And if they know, can they determine if the dies being made in their own mills have the proper specifications? Do your die refinishers get away with producing inferior dies because of a lack of real supervision? A draw bench or block is no better than the die. The machine serves only to make the die effective. Therefore, the die must be designed properly and then finished to that specification which works best for the particular type of steel being drawn. That specification depends on a lot of things, some characteristic to a particular mill. Yet a lot of dies being used are not designed or finished properly. Most of them work, but they could work a lot better and last a lot longer. Our company is also in the business of marketing die finishing equipment, and it is common when giving demonstrations to see people's mouths drop open when they see what their die contours actually are compared to what they thought they were. Take a die out of your die rack that has supposedly been reworked and check it. There is a good chance it is way out of spec. So to repeat myself a little, why are dies like these made? Ignorance on the part of supervision as to the importance of good dies and what constitutes a good die. This situation exists because people that should do not know much about dies, and those that do know are too busy to get into the die situation. 2. Poorly trained die finishers. Poor die finishing practices are permitted to exist, and die finishing equipment is obsolete or in poor condition. If we're going to keep the cold finish bar industry alive in this country, we are going to have to upgrade the state-of-the-art of carbide dies so they are better understood. You must upgrade your die technology in order to operate more efficiently and improve your finished product. It is being done, and where it is being done, these mills produce fantastic quantities at fantastic speed. The secret, good tooling. Now, there are other important areas to cover in the state of art and new developments in carbide dies. We'll first cover die design. A common problem in the design of many bar dies is that there is not enough angle to assure the proper contact of the entering stock in the die. The entering stock should contact the die approximately midway in the approach angle. This makes certain there is enough angle above the draft line to build sufficient pressure for effective lubrication, yet allow enough area in the die for the reduction to take place. This conical angle directs lubricant into the die, compacting it on the bar as it is drawn. Therefore, to obtain good or exceptional die life, there must be enough length of angle to force lubricant into the die. Ideally, the angle above the draft line provides for effective lubrication, while the remaining area of the approach angle reduces the bar. Then, the approach angle can be varied depending on the amount of draft. If the reduction is heavy, the angle should be opened up, or better yet, as in this illustration, the nib height increased to lengthen the approach angle in order to provide for proper contact on their entering stock in the die. This is very common today in hex dies. Most all of your die suppliers stock special height hex die nibs to accommodate common problem of oversized hot roll. We see many cases where problems are caused by the incorrect contact of the stock and the die. Light drafts are taken using approach angles which allows the entering steel to contact the die too close to the bearing, as seen on the top view. This reduces the stock too quickly. When taking light drafts, angles should be altered to accommodate proper drafting, as in the bottom view. Drafts take place too far up the die, which can actually repel the lubricant, and where the contact is outside the drying angle, pickup occurs immediately. This is a common occurrence when using oversized hot roll. If the entering stock contacts the die properly, you achieve the advantages of improved lubrication, lower drying temperatures, reduced drying forces, more uniform flow of the metal, increased drying speeds, and improved bar quality. Bearing lengths should be parallel with blending where necessary. The top view shows a tapered bearing. With a tapered bearing, the metal is also reduced in the bearing. In normal drawing, the bar should be reduced in the approach angle, and the function of the bearing is to control the size only. Die maintenance. As previously mentioned, many die finishing techniques and equipment in the majority of die finishing operations are antiquated. Too many dies are hand work. This destroys die angles and bearings. When it comes to round dies, the reworking of dies should be by machine, not hand, except for necessary blending. Here is a modern grinder specifically designed for finishing approach angles in bearings for dies in 4-inch cases and smaller. This is a state-of-the-art machine to make it easy for mills to maintain dies. Anything more gets very expensive, and we firmly believe it is much less expensive for bar mills to purchase finished dies on the outside and use their die maker or die rooms to maintain and resize dies. Outside die suppliers have the automatic equipment and skilled die makers to do the job quickly and furnish quality dies. Mills generally do not, nor can they afford the necessary equipment. This is not to degrade die finishing in mills, because we feel it is necessary in all mills to be able to perform die maintenance, and why we furnish equipment for it. Our point is that the state of the art in die finishing has progressed to the extent of making it unaffordable for mills to maintain fully staffed die rooms. Die making has gone to the computer age. Computerized numerical control machines are common. In finishing rounds, we may have one man operating two $60,000 automatic grinders and at the same time doing the necessary hand blending and polishing in and on another machine. In shaped dies, it is worse. The present state of the art has progressed to $150,000 wire-cut EDM machines to manufacture shaped dies, plus thousands of dollars in auxiliary equipment is required. We see great inefficiency at bar mills that still maintain fully staffed die rooms. By cutting back, the labor costs saved will, in many cases, pay for the outside die costs and assure your mill of getting quality dies. The present, and most importantly, the future state of the art is passing the die makers in your mills by, and the very nature of the system prevents many mills from getting good die people to do their die finishing. That covers one aspect, and now we'll progress to shape dies. In cold finishing, besides standard hex and squares, there has been an explosion in the drawing of special sections. Most all of you are involved. Basically, there are certain points to understand regarding shape dies. It is exacting and very unforgiving. If conditions are not right, you are in trouble. Material will not always draw to the shape or size required, even if the die is on size. Often, die angles and contours have to be changed to help more metal move into a particular corner radius or to fill a lug. A lot can be done with die design to help, but the first rule in shape drawing is that you must have enough metal available in the entering bar to fill the shape section. This creates problems because to use available hot-rolled material, several or more passes may be necessary. Or, even if you can use available hot roll, the drafting is such that terrible stresses are built up in certain areas of the die. This point is mentioned because we still see attempts to move metal into areas that will never flow in cold drawing, thereby creating many die problems. Drafting is very important to successful shape drawing. When drawing shape to shape, where the entry stock is in the same form as the die configuration, standard reductions can be followed. But in drawing rectangular bars, the draft on both dimensions should be proportional with an even reduction on all four sides. If an equal reduction is not taken, as is often the case, an adjustment must be made to the die angles to allow the entering stock to hit evenly. In a rectangular die, in order to get full even contact around the perimeter of the angle, the approach must be varied on two of the flats, as seen in the bottom view. The drawing of special shapes from round the drawing of special shapes from rounds is difficult. Shapes that contain grooves or splines require special die geometry. Correct design of the approach angle is critical to the success of the draw. The starting round should begin drawing above the lugs, as in this example. A typical D-section die, if made from a round, must be designed with a wider angle on the flat to accommodate the entering round. As previously mentioned, there is a tendency for bar stock to draw to dimensions other than the die size. This is particularly true for irregular or intricate shapes. A common example of this problem is underfill, the material not filling out the die as it is drawn. This occurs in round-cornered rectangles, hexes, squares, groove sections, lug dies, and so on. Causes for dies not drawn on size are improper entering stock, improper drafting, poor approach angle design. Of these three, the last is the most frequent. The design of the approach angle must help the bar fill to the desired shape, not hinder it. Therefore, approach angles must be designed to aid the flow of the metal into the proper areas. In radius-cornered squares drawn from sharp-cornered material, the corners in the die angle must be altered to allow the entering stock to fit the die properly. When uneven drafting takes place, die angles must be modified to help equalize the reduction. Non-uniform pressures build up in dies during drawing is one of the prime causes of fracture and lubricant failure. Designing approach angles of shaped dies with projecting lugs is another difficult undertaking. There are various ways the lug can be designed in the die. They can come straight up the angle, as in this example, taper in or out, get smaller or larger, remain sharp, or be radiused. Should the stock first contact the lug, or should it first make full contact in front of the lug? All of these things must be considered, and depending on the application, experience, type of metal, and so on, different designs are used. Just because the bearing form of a shape die is correct, there is no guarantee that the die will draw to the desired shape. How the approach angle in the die is constructed is critical. The outside corners of lugs or other projections in shape dies can cause drawing problems. They tend to pick up, wear, and break easily. These projections should be designed with as much radius on the corners as possible. Any sharp 90-degree corners will be a weak point in the die. Ordinarily, a lug or projection takes a heavier load than the other areas and must be given as much help as possible to make it stand the strain. Metal pickup is not uncommon in drawing shaped or round bar, although the chances are greater when drawing intricate shapes. Several reasons for pickup are heavy local reductions or lack of adequate lubrication pressure due to uneven die contact. Multiple pass operations present special problems. They can carry a defect over to the succeeding pass when the actual cause is from the initial draw. The solution then necessitates modifying the first pass die contour. Therefore, troubleshooting cannot be confined to the draw pass where it is occurring. Mistakes are continually made in shape drawing. The hot roll is not measured. The way it fits in the die is not checked. In drawing from rounds, large enough stock is not used to fill the corners, lugs, and grooves. Sometimes this is not discovered until all the first or even second pass stock has been drawn. Too heavy reductions are taken in certain areas, guaranteeing die breakage. Dies are not properly maintained. Pickup is not removed, particularly in critical areas, like in front of lugs. Hand working of shape dies by die makers ruins die contours. Mill supervisors must constantly monitor their shape drawing procedures to avoid these type errors. Once an expensive shape die has been damaged by carelessness, not much can be done to save it, and a replacement cannot be quickly furnished. Now, let's get into something that's new, and I think it'll be of interest to everybody: round to hex drawing. One of the biggest cold drawing developments in recent years to improve the state of the art is the development of drawing rounds to hex in one pass. The development of a special die design has made this advancement possible. This is your standard hex die as seen from the front, looking into the die. It has a flat hex approach angle designed to accept hex hot roll. In round to hex, a special approach form is needed to achieve reasonably sharp corners. Drafting is based on having large enough starting material to produce a finished hex with a sharp corner. The entering round must contact the full perimeter of the angle above the petals, as shown by the dotted line. This full contact improves the lubrication of the bar that helps prevent scratching in the finished bar and excessive die wear. The petals act to aid in the transition from round to hex and help move the material into the corners of the hex. Also, the intersection between the petals and bearing of the die must be kept sharp in order for the corners to fill. As the sharp intersection wears away during drawing, the corners of the drawing bar become less sharp, and as the top of the petal also wears, the die will begin to draw undersize. The worst thing to do is open up the die, as some of you have learned the hard way. When these conditions occur, the die must have the petals reworked and the intersection sharpened. This is a job for the die supplier, as it is done by machine, not by hand working the die. Normally, round to hex dies can have the petals reworked several times before the die has to be taken to another size. Petal hex dies are more expensive than standard hex dies, but the advantages of being able to use round stock far outweighs the added cost. So far, the main drawback has been the problem of being successful drawing sizes over 1 inch. Solid versus sectional dies. This is a dispute we will not solve, but rather point out the advantages and disadvantages of both, and then render an opinion on where the state of the art is going. Generally, small rectangles are drawn in solid dies, except several mills use side end block setups for all their flats, and others use solid dies all the way, while most mills use a combination of solid dies and side and end blocks. They both work well, and you can argue the merits of either system. The advantages of side and end blocks: sharper corners, The pieces can be reworked and used over and over, particularly the side blocks. Within limits, the size can be adjusted. Larger sizes are obtainable within the head size of a draw bench, and the size-price ratio improves as the sizes get larger. This end block print is of a pretty typical design. The draw radius is thrown off center to allow sufficient top opening to accommodate the entering flat stock. There are also many variations of this design. Some blocks are designed with actual angle and bearing forms, which make them more like solid dies, but also more difficult to fabricate and maintain. Note the thickness of the block. Increasing this thickness to 1.5 inches or even 2 inches, particularly in side blocks, improves the strength of the carbide to help prevent breakage. The advantages of solid dies: less setup time, easier to draw, better die geometry, multiple drawing is possible, better for long runs, easier to handle, and easier to push point. Except for the initial expense of a sectional die setup, the cost of sectional dies compared to solid dies is pretty close. You can see there are advantages to both systems. The best system in today's state-of-the-art is a combination of both solid dies and sectional dies. Use solid dies as large as you can go, and then switch to sectional dies. At present, this is generally in the 3-inch range with solid dies. However, because of setup time, adjustment time, and the amount of space required for sectional die setup, we see a move to solid dies. The big reason is the multiple draw possibilities using solid dies. The cost of operating new big benches is such that the multi-drawing of large flats is required and appears to justify the solid die cost. Therefore, as bigger benches are built, more solid dies will be used. Now we would like to talk about some of the improvements in the state-of-the-art regarding the material itself, tungsten carbide. Basically, your straight grades of carbide are still the best for cold drawing steel bars. Several standard grades of 9%, 13%, and 15% cobalt content are used. The rule of thumb is that as the size of the bar to be drawn increases, a higher cobalt grade of carbide is used. Cobalt is the glue that holds the tungsten particles together. Therefore, the more you increase the cobalt content of carbide, the stronger it becomes and less apt to break. However, conversely, as the cobalt content increases, the hardness of the material decreases. This slide shows a relationship between the hardness and cobalt content. The vertical line is horizontal. The vertical line is the hardness, and the horizontal line is cobalt, increasing in percentage from left to right. As you can see the straight line relationship, as the cobalt content of the carbide increases, you can see how the hardness decreases. Abrasive wear is also a factor. Here we see the relationship between abrasive wear and cobalt. And the abrasive wear basically is the bar wearing the carbide as it passes through the die. The higher the cobalt content, the greater the wear and the lower the die life. Other factors such as grain size affect the carbide, but nothing affects the physical properties as drastically as the cobalt content. Yet, since high cobalt grades are stronger and less likely to break but wear, one recent development has enabled us to make larger wear-resistant carbide dies. That is the use of larger particle sizes of tungsten in combination with high percentages of cobalt. The larger particles wear better, and the high cobalt content gives the die strength. In very large carbide dies costing thousands of dollars, this has worked well. Another improvement has been hot isostatic pressing. Hot isostatic pressing is the additional processing of a previously centered preformed part by the application of high heat and isostatic pressure via compressed gas, usually argon. Hot isostatic pressing, or HIP it is generally referred to, is it intended to reduce the normal low porosity in good quality hard metal virtually to the vanishing point. One purpose is to ensure that no defects appear on polished working surfaces. This is extremely important in rolling and drawing applications. A second effect of HIP is a claimed improvement in strength. It has become a rather standard procedure to hot iso large carbide dies. We look at it as an insurance policy to help eliminate porosity and increase strength. The previous speaker briefly touched on coatings for cutting tools, and I think we can briefly cover some of the coatings in carbide dies. The most popular coating, and the one that has shown the best results in our opinion, is titanium nitride. This is a thin coating of titanium nitride over the carbide. Titanium nitride is harder than tungsten carbide and therefore should be more wear resistant. A lot of other materials have also been tried, most of them being in the ceramic family. They are zirconium oxide, silicon carbide, and silicon nitride. If you talk to the manufacturers, they claim they are terrific. We cannot criticize these products because someday someone will develop a better die material. A present and foreseeable state-of-the-art prediction regarding coatings and other die materials is that in certain situations they offer an advantage. However, it is doubtful that, in spite of the development of newer die materials, the carbide die will be replaced in the foreseeable future. When properly designed, finished, and maintained, carbide dies can withstand the challenge of most any substitute material. The unique properties of tungsten carbide, its high hardness and durability, together with a reasonable price structure, are a combination that assures the carbide die of a lasting and vital role in bar drawing. We hope this presentation has made you aware of some of the problems we see and how dies are handled in the mills, and given you some insight into the things that will prove the understanding and use of carbide dies in your bar mill.
Well, thank you very much, Ken, and we'll entertain questions from the group here in Pittsburgh.
Normal rule of thumb, let's use an inch with a 16th draft, and you manufacture a round die for that draft. If you were to take a 30-second draft or a 3/32 draft, would you expect that die to perform well, and you wouldn't worry about changing until you went, say, to an 1/8 inch draft or something like that?
No, not at all, because as that slide showed, if you're going to take a 30-second draft, you better tighten that angle, because if you don't, most likely that entering stock is going to hit right actually in the bearing of the die or on the blend, and you end up just pulling over a real narrow or tight angle, and you're actually scraping through there rather than cold drawing. Vice versa, if you're going to take an 1/8 of an inch draft, as Mr. Mayor mentioned in talking about where it should hit, you should have a die designed so that 1/8 inch draft is not hitting up in the bell of the die or right in the mouth of the die at the top of the angle, so that different dies should be used for different drafts.